Nothing beats. In this video, we're going to talk about derivatives of exponential functions. We're going to come up with the general derivative of an exponential function. Let's go. All right, the first thing we're going to do is first recall the inverse properties of logarithmic and exponential functions, because as we're going to see, we'll need these to come up with the formula. All right, now, as is the case with all exponential and logarithmic functions with base b, remember, throughout this conversation, we're always assuming that the base is positive and it's not equal to 1. So having said that, here's our inverse properties here. Let's just kind of quickly go through these. Now this first one, part A right here, say you have this formula x is b to the y. Then literally y is equal to the logarithm of base b of x by definition. In other words, exponential functions and logarithmic functions of base b are inverse functions of each other. And when you compose inverse functions, you get back the input, assuming that, of course, it satisfies the conditions that are needed. So that's what the second two properties are about right here. Recall that if I raise a base b to the logarithm of base b of x, I get back x, and that's always true just for positive x because, of course, the x is being inputted into the logarithm first. Whereas in part C, the logarithm of base b of the function b to the x, composition of inverse functions, also gives us x, but in this case that's true for all real numbers x since b to the x is always positive. So those are our inverse properties. And now, of course, the goal is to figure out what's the derivative of a general exponential function, b to the x, with respect to x, assuming, again, the base here, b, is positive and not equal to 1. Well, remember, we already have one of these established. This one specific derivative, the derivative of e to the x, is, of course, e to the x, as we've established. So we're going to use that along with the inverse properties to come up with our general formula. So note that the function here, b to the x, can be rewritten equivalently as e to the x times the natural log of b. Now, why is that? That's because I can rewrite e to the x times the natural log of b as e to the natural log of b quantity to the x, right? Just multiply those powers there, and by inverse properties, e to the power of natural log of b is just b, so as you can see, b to the x is indeed e to the natural log of b times x. So let's use that. Let's use it to come up with our general derivative. And that is, if I want to differentiate b to the x with respect to x, that is the same as differentiating e to the power of x times the natural log of b with respect to x. And that's a chain rule, e to the function power. So a chain rule says, take the derivative of that function power, derivative of x times the natural log of b with respect to x, times e to that power, the derivative with respect to x of x times the natural log of b, is just the natural log of b, and thus, what do we get here? We get our formula that this is just natural log of b times e to the power of x times the natural log of b, but of course, e to the power of x times natural log of b is just b to the x. Thus, we get natural log of b times b to the x. That's our formula right there. That's our derivative of any general exponential function, b to the x with respect to x. So add it to the list. Maybe take note here. Note, if b equals e, then the natural log of e times e to the x is, of course, just e to the x. And the derivative of e to the x, of course, is e to the x, as we've established. So the point I'm making here is that e is included in those bases, right? It's that special case. So we got the rule now. And so what we're going to do is just finish off the video by looking at a couple of examples. let's go ahead and find some derivatives. So this first one, part A, just to see the basics here, we're asking to find a derivative of 5 to the x with respect to x. So the formula says, as we just established, natural log of the base, natural log of 5, times 5 to the x. That's it. That is the derivative. So you see it. Let's do another one, though. How about the derivative of tangent of 3 to the t with respect to t? Well, this is a chain rule. Tangent of a function, so that means I got to differentiate with respect to t, 3 to the t. That's that derivative of the inner function with respect to t. Derivative of the outer function is the derivative of the tangent function, which gives us a secant squared function, and leave that inner function. Finally, here's our derivative of our exponential part. Derivative of 3 to the t with respect to t is natural log of the base, natural log of 3, times the exponential function 3 to the t, times here secant squared of 3 to the t. And there you go. Another example. One more and we're done. All right. How about this one here? How about find the derivative with respect to w of the product of sine of w times the root of 7 to the w? Now, for the sake of simplicity here, I'm just going to rewrite this as sine of w times 7 to the w all to the half power. But by properties of exponents, that's the same thing as the derivative with respect to w of sine of w times 7 to the 1/2 w power. Now that's not completely necessary, but it does help in our algebraic manipulations throughout this process. Now, having done that, let's go ahead and apply our product rule here. So product rule says this is going to be sine of w times the derivative with respect to w of 7 to the 1/2 w power plus 7 to the power 1/2 w times the derivative with respect to w of sine of w. There's my product rule step. Now I'll differentiate. Notice that 7 to the power of 1/2 w is another chain rule differentiation. The derivative of 1/2 w with respect to w is a 1/2. So we get a 1/2 times sine of w. And then times the derivative of the outer function there, which is that base 7 to the power. So we get an ln of that base, ln of 7, times that function, 7 to the 1/2 w power, plus a 7 to the 1/2 w power, derivative of sine function, of course, just the cosine function, so cosine of w. And because I can, why not just factor out a 7 to the 1/2 w power? And what are we left with? We're left with a 1/2 natural log of 7 sine of w plus a cosine of w. And there we go. There is our derivative in this circumstance. And that's it. That's this video. So the video, of course, was designed to come up with the general rule for derivatives of exponential functions. We did that. We did that by, of course, first reminding ourselves of the inverse properties of logarithmic and exponential functions. We use those properties to rewrite an exponential function in a special form so that when we then went and differentiated, we can apply the chain rule. And we came up with the result. Derivative of b to the x with respect to x is the natural log of b times b to the x. And now you have a few examples to go off of too. So that's it. In the next video, we're going to come up with the derivatives of logarithmic functions. So until then, you know, it's Madden Beats, so might as well be out. I'm out.